This is Control-Alt-Break from the studios of Greyhead Digital. Catch the trends, news and all that matters from the world of technology.
There was a lovely article from Wired magazine that caught our attention. An excerpt there read, and I quote, "In 2016, Google announced that its D-Wave computer had outperformed a traditional desktop by 108 times, making it 100 million times faster," unquote. Hartmut Neven, the director of engineering at Google, said that what a D-Wave could do in a second would take a conventional computer 10,000 years to do. Fascinating. What is a quantum computer? Hello and welcome to Control-Alt-Break, your daily podcast from Greyhead Digital on everything from the world of technology. My name is Ashwin Raghunath, and let's dive in. Classical computers operate on a binary scheme. One example is the two-state deterministic system in which a series of zeros or ones encode information. Quantum bits, or qubits, are the basic units of quantum computing. Unlike a bit, which can only be in a 1 or a 0 state at a particular time, a qubit can be in a 0 state and 1 state simultaneously. The power of a quantum computer comes from that unique feature of quantum system, because of which harnessing the quantum physical behavior increases computational power exponentially when solving certain types of problems. And this empowers quantum computers to process information in new ways. Now, many top leading companies like Google, Microsoft, and IBM are heavily investing in it due to the huge power quantum computers could potentially unlock. Now, the so-called weirdness of quantum mechanics, where basic laws of physics break down, have potential to solve many long-standing problems. However, like everything else, it has a downside as well. The arrival of powerful quantum computer poses severe consequences to cryptography. This is especially true of public key encryption, which protects our internet security and powers e-commerce. As we know, securing internet traffic is based on asymmetric encryption using TLS. RSA and elliptic curve cryptography are two asymmetric encryption schemes that play a crucial role during a TLS handshake. As TLS is the foundation of the network transport layer security of internet traffic, it is easy to imagine the chaos that may ensue if the encryption behind TLS is no longer trustworthy. The quantum speedup yields many mainstream cryptographic algorithms, that is RSA, DSA, ECDH, vulnerable to attack. The potential negative consequences are severe given the ubiquity of asymmetric encryption. Now imagine a day without safe cryptography. In 2015, the US National Security Agency, the NSA, recommended a pause of migration to Suite B cryptography during the growing concerns that Suite B, which includes AES, ECDSA, ECDH, and RSA 3072, might not be quantum resistant. This announcement, perhaps more than any other, brought attention to quantum computing cybersecurity threat. The statement read, and I quote, "Corporations housing sensitive information meant for long-term concealment may face quantum attack, so planning must be put in place now to mitigate, harvest, and decrypt attacks." So what can you do? Here's a few preparation steps for post-quantum era recommended by the Cloud Security Alliance in a white paper. Firstly, acknowledge the severe impact of powerful quantum computer on cryptography. This acknowledgement is a precursor to active mitigation of quantum computing risks. 2. Inventory impacted IC assets. The powerful impact of quantum computer on each of these assets, and we're talking about servers, laptops, mobile devices, network appliances, these are all very different, and each asset requires an independent assessment. One component especially impacted is the public key infrastructure, where certificate authorities provision digital certificates while certificate management systems manage the certificates. Another sensitive application relates to data center connectivity, where large amounts of data flow between one data center and a backup location. Safeguarding this data now and into the future is paramount. And finally, pursue cryptographic agility. Now, cryptographic agility refers to how nimble an organization is to replace existing crypto algorithms with newer ones. Software frameworks such as .NET Cryptographic Service Provider or Java Cryptography Architecture, these provide object-oriented classes supporting a wide range of algorithms, modes, and key sizes. Developers should avoid hard-coding algorithms and key sizes in their source code. Using these classes and externalizing algorithm names and key sizes in configuration files facilitate crypto agility. Finally, it is unclear whether a large-scale, publicly accessible quantum computer is buildable, according to the NASM report on quantum computing. Therefore, an accurate quantum computing development timeline is not currently possible. However, because public key cryptography plays a vital role in the IT infrastructure of all our enterprises, it is prudent to acknowledge the emerging cybersecurity risks posed by quantum computing and plan accordingly today. Scary or fascinating? If you're already dabbling in this space, we'd love to hear from you. Catch us on LinkedIn at Dynamic CISO, follow us and leave us a line. Till tomorrow, this is Ashwin signing off for Control Alt Break and Greyhead Digital.